We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Get my feet out. Okay, I'm out. Well, it looks funny out there. See my glove out there, Jim.
Jimmy Moore, get that yet. Good morning, Gordo.
Yes, how are you?
How does it feel for the United States to be the new record holder?
At last, huh?
We're rolling up and we can't turn anything off. Finally increasing in a low roll.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 77 of the Space Rocket History Podcast. And now, Gemini IX-A with Tom Stafford and Gene Cernan. After the untimely deaths of Elliot C. and Charles Basset, NASA assigned the Gemini 9 prime crew positions to Tom Stafford and Gene Cernan. This was the first time in NASA's manned spaceflight history that a backup crew had taken over a mission. The capsule was renamed Gemini IX-A. On March 21, 1966, Jim Lovell and Edwin Buzz Aldrin were assigned as the backup crew for Gemini IX-A. There would be no delay in the launch schedule. Now for some biographical information on the crew of Gemini IX-A. This would be Tom Stafford's second Gemini flight. His first was Gemini IX-A. His biographical information can be found in episode 65. Stafford was assigned the command pilot's position on Gemini IX-A. Now moving on to Cernan. Eugene A. Cernan was born in Chicago, Illinois on March 14, 1934. His father was Slovak and his mother was Czechoslovakian. Cernan grew up in the suburban towns of Bellwood and Maywood, Illinois. He attended Proviso East High School in Maywood and graduated in 1952. After high school, he entered Purdue University, where he became a member of the Phi Gamma Delta fraternity. He received a Bachelor of Science degree in Electrical Engineering in 1956 and was commissioned as a U.S. Navy officer through the Naval Reserve Officers Training Corps at Purdue. He entered flight training upon graduation. He was assigned to Attack Squadron 26 and 112 at the Miramar, California Naval Air Station, and subsequently attended the Naval Postgraduate School. He became a naval aviator, flying FJ-4 Fury, then A-4 Skyhawk jets. He logged more than 5,000 hours flying time with more than 4,800 hours in jet aircraft and over 200 jet aircraft carrier landings. He also earned a Master of Science in Aeronautical Engineering from the Naval Postgraduate School in 1963. Cernan was assigned the pilot duties for Gemini IX-A. Flight Director Gene Kranz wrote that Cernan was his favorite because of his carefree and jovial attitude, unabashed patriotism, and his close personal relationship with the flight controllers. Gene married Jan Nana, and they had 3 daughters. His hobbies include love for horses, all competitive sports activities, including hunting, fishing, and flying. Now let's move on to the preparation for Gemini IX-A. By the spring of 1966, the delays in preparing for Gemini missions were diminishing. Vehicles were now getting to the Cape about a month before they were needed on the launch pad. The NASA Air Force industry launch teams had gained plenty of experience in reacting quickly to Gemini hardware problems. Merritt Preston, one of NASA's leaders at the Cape, is quoted as saying, quote, "Habitually, we got into trouble on Gemini, but it never got to us because we could always fix it." End quote. Gemini 8's thruster failure turned out to be a blessing in disguise. As the Cape workmen carefully inspected the adapter area around the thrusters on Gemini 9-A, they found a number of likely causes for the malfunction, which they adjusted on the spot. Meanwhile, in St. Louis, engineers were exploring ways of dealing with the electrical short in the thruster circuit. The Gemini Project Office and McDonnell decided on a master switch that would cut off all power to the thrusters simultaneously. In case of trouble, the crew could check the circuit breaker by circuit breaker, until a short was found. The Cape team installed this switch on Spacecraft 9 with no effect on the launch schedule. So, for the Gemini 9-A mission, the three major questions centered on working procedures rather than technology. The first question was tethered versus untethered extravehicular activity. Work on the Astronaut Maneuvering Unit, also called the AMU, by the Air Propulsion Laboratory at Wright-Patterson Air Force Base in Ohio, set the stage for the tether debates. The AMU was powered by a hot gas, hydrogen peroxide. In a number of tests, the device showed it would be useful to an astronaut in controlling his attitude and keeping himself stable while he maneuvered in space. When early in 1963 the Air Force was given a chance to place experiments in the Gemini spacecraft, the AMU was an obvious choice. It could help pilots working in space on many tasks that the Air Force was particularly interested in: maintenance, repair, resupply, crew transfer, rescue, satellite inspection, and assembly of structures. Since none of these was as yet a primary or secondary objective to NASA, the unit would fly in Gemini merely to confirm what it could do. The tether entered the picture as a safety factor. At first, the Air Force had in mind a 60-meter tether, but studies suggested that an astronaut might get tangled up in a weightless tether. Although this might be countered by a real mechanism that would keep the line taut, the real question soon became whether a tether was needed at all. Could redundant or alternative systems offer the same safety provided by tying an astronaut to an orbiting spacecraft? The Air Force thought they could, and some in NASA agreed. Tether development was canceled. Colonel Daniel McKee, head of the Air Force Field Office in Houston, pointed out that when contractors understood that astronauts would not be tied to spacecraft, they would be compelled to make a highly reliable system. After all, no one wanted an astronaut floating off into space. But that possibility was exactly what NASA was worried about. Warren J. North, chief of MSC's Flight Crew Support Division, held that tethers were a spaceman's best friend, especially if you have oxygen in them. The dispute persisted, sometimes heatedly. At a MSC and Air Force meeting in July 1965, NASA headquarters made its official position quite clear. William Snyder, Deputy Director of Missions Operation, wired MSC Gemini manager Charles Matthews that EVA shall be based on the use of a tether on all Gemini flights. But Colonel McKee was not so easily discouraged. In February 1966, he was still debating the issue. McKee wanted the matter left open until Gemini 12, when the maneuvering unit was scheduled for its second flight. He prepared a position paper pointing out that all critical systems on the AMU were backed up and that its test programs had been oriented toward free flight, because this was the unit's ultimate purpose. MSC Director Robert Gilruth forwarded McKee's case to George Mueller, chief of NASA's manned spaceflight programs, who was still not convinced. Mueller insisted that all Gemini astronauts would be tethered, but even this experience might be helpful to the Air Force in future untethered flights. A new NASA position paper describes spacecraft maneuvers that would maintain tether slackness to simulate free space activity. Here is a quote from the NASA position paper. Quote, "Prudence dictates that a tether be used at all times during Gemini extravehicular activity. The door might still be open to untethered flights in the event that an operational requirement is identified that cannot be met in any other way." End quote. The spinning flight of Gemini 8 on March 16th gave the Air Force a chance to push that door open. What might have happened had Dave Scott been outside and fastened to the spacecraft when it went out of control? He could have been wrapped up like a broken window shade. The Air Force suggested adding a safety disconnect device so a crewman could free himself if something like that happened again. NASA officials, too, had been thinking about the plight of a crewman caught outside a whirling spacecraft. Scott said that he could have spotted the thruster problem and gotten back into the spacecraft to help Armstrong deal with it. But many in the Office of Manned Spaceflight were convinced that if spacecraft troubles arose when a pilot was outside, the best thing for him to do was to get back inside as quickly as he could. There were too many hazards connected with troubleshooting for him to try diagnosing any problem, let alone using a disconnect to discard the security of a lifeline. That ended the active debate, but there were still some who thought it was a good idea, one that ought to be tried in future programs. The second major issue on the Gemini 9A mission was when to rendezvous with the target vehicle. Planners for Gemini 6, considering possible sources of trouble, had concluded that rendezvous should take place no sooner than the fourth orbit. This was a well-researched procedure which Wally Schirra and Tom Stafford had demonstrated in high style in Gemini 6A. But some engineers in the Apollo spacecraft program office wanted to tamper with success. Rendezvous in the first, or at least by the third spacecraft revolution, would more closely approximate lunar orbit rendezvous. In September 1965, mission planners began working on a tentative rendezvous in the third spacecraft orbit for Gemini 9A. For the rest of the year, they worked on this new rendezvous scheme. NASA, Air Force, and industry representatives met in Houston on January 20, 1966, to review the results of these labors. After the spacecraft had separated from the launch vehicle, the first maneuver, called IVAR, which stands for Insertion Velocity Adjustment Routine, would reduce orbital insertion errors. The crew would use the inertial guidance system to raise or lower spacecraft trajectory immediately. At the apogee of the first circuit, the crew would perform a phase adjustment to establish the proper phase relation between the spacecraft and the agena. 1.5 orbits later came another change, this time a triple maneuver, to correct phase, height, and out-of-plane errors. The final maneuver was to circularize the flight path 2.25 revolutions after insertion. This would place the spacecraft about 28 kilometers below the target and ready to start firing to catch it. The remaining maneuvers were similar to those required for a fourth orbit rendezvous. No one doubted that this sequence would work, but some saw no reason for rendezvous on the third orbit at all. Two camps formed. One group insisted that it closely approximated lunar orbit rendezvous. The other maintained that the kinship was so slight that it was not worth doing. The second group also contended that ground tracking and ground computer capabilities for this approach were not as good as they were for rendezvous in the fourth revolution. Deputy Director of Missions Operations Snyder believed that the third circuit concept would be useful to Apollo operations. Mueller agreed with him, and that settled the issue. The third Gemini IX-A issue was whether to use radar versus optical tracking. This grew from a type of rendezvous clearly applicable to Apollo. This matter first came up when several engineers looking for ways to keep the spacecraft from getting too heavy wanted to pull the radar out of both Apollo vehicles. The command module lost its radar in February of 1965 when the ASPO Configuration Control Board ruled that the astronaut aboard the mothership could use an optical sight to help rendezvous with the radar and flashing light equipment on the lunar module. Later that year, with weight reduction becoming even more pressing, the lunar module's radar was the candidate for removal. This meant that during lunar operations, whether on takeoff from the moon or at any time the two vehicles were apart, rendezvous of the two ships would depend entirely on the astronauts' eyes, optical sights, flashing lights, and computers. This was too much for the astronauts who had to fly the machines. They did not entirely trust their eyes or the suggested equipment. They wanted the help of electronic radar signals on one vehicle bouncing back from the transponder on the other. At least, they said, the radar should remain on the lunar module. Stafford and Cernan did agree to include a test on Gemini IX-A to compare optics and radar by performing a rendezvous from above the target vehicle. In this exercise, the Agena would be over the Sahara Desert, which would simulate the lunar surface, and the crew would try to fly down to it using both radar and optics. So, this third issue would remain open. With most of the debated questions settled, we can move on to the mission objectives for Gemini IX-A. The primary objectives were to perform rendezvous maneuvers and dock with the target vehicle, and to complete the often postponed EVA maneuver. Secondary objectives included, first, rendezvous with the target vehicle in the third orbit to closely simulate the Apollo requirements. Second, conduct systems evaluation and perform an equi-period rendezvous using onboard optical techniques. An equi-period orbit is shaped similar to an American football or an ellipse. The equi-period rendezvous was designed as a fuel-saving method to evaluate maneuvers and light conditions for a dual rendezvous with a passive target. The third of the secondary objectives was to execute 7 experiments. Fourth was to practice docking. The fifth, rendezvous from above to simulate the rendezvous of the Apollo command module with the lunar module in a lower orbit. And sixth, demonstrate controlled re-entry. On May 17, 1966, everything was ready for Gemini IX-A. In the Mission Control Center, Gene Kranz assumed his duties as flight director, presiding over a 3-shift operation. The other 2 flight directors were Glenn S. Looney and Clifford Charlesworth. Only 200 newsmen were on hand, compared to the 1,000 or more who had covered Gemini 4 the year before. Gemini was becoming more routine and hence less newsworthy. After a smooth countdown, Atlas Launch Vehicle 5303 rose from Pad 14 at 10:12 a.m. For 2 minutes, the rocket's 3 engines rammed a Gemini 5004 skyward. Here's the clip.
Time down. There could be a brief hold at the 19-second mark as the sequencer is put into effect. The engines on the Atlas will ignite at the 4-second mark in the countdown. And at about the 0 mark, we will get liftoff with full thrust of those 3 engines at the base of the Atlas vehicle. That is, the sustainer and the 2 booster engines give us a total thrust of 390,000 pounds. Now, just passing the 2-minute mark on the Atlas Agena count. At this point, the range safety commands have gone on internal power in the vehicle. Our final phase of checkout is still looking good at this time. T-minus 90 seconds and counting. T-minus 90 seconds and counting. The Atlas vehicle is completely on internal power at this point. Now 1 minute and 15 seconds away from Atlas Agena liftoff. This is Gemini launch control. T-minus 60 seconds and counting. T-minus 60. T-minus 50 seconds and counting. At this point, the launch vehicle test conductor has a series of lights on his console. They will all turn from amber to green as the count continues. This is not automatic. T-minus 40 seconds and counting. T-minus 30 seconds and counting, and our final check still give us a go condition at this time. T-minus 20. T-minus 19, 18. 18 holding momentarily. T-minus 15 seconds and counting. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. It looks good. It's a beauty. Up through the clouds. That's the 1,800-foot level. 32 seconds. Beyond. Almost straight above us, it seems here now. Still looks good. Should have begun its pitch about 30 seconds ago and has begun to pitch over. Flight Dynamics says the trajectory looks good. Following exactly the overlay of our clockboards here. At this time, the Agena is about 3,000, moving at 3,000 feet per second. Trajectory is still looking good. Agena is about 15 miles, 17 miles in altitude, and is approximately 18 to 19 miles downrange. Liftoff took place 15 minutes and 3 seconds after the hour. The booster engine has cut off. Control, we had a temporary loss of data. It is coming back in now. Control, according to our clockboards, we do not as yet have second stage ignition. Our flight dynamics officer just reported to the flight director that he believes we have second stage ignition. T+3 minutes and 20 seconds. Data on our clockboards here at Mission Control. T+4 minutes and 10 seconds. We have lost the data on our blackboards here. Our flight director, Gene Kranz, is attempting to raise the range safety officer at Cape Kennedy, as yet with no success. We're passed on by flight dynamics. The range safety officer, we understand, says we are flying low with the Gina and may come in. We have a report now of second stage ignition. Seco was second stage cutoff, not ignition. Gina advises we have had ECO, vertical engine cutoff, and separation. Here in Mission Control, our blackboards do not give us the data that we need to report to you. We are now 5 minutes and 50 seconds into the mission. 6 minutes, 20 seconds. We still have no actual word on the condition of our bird. 6 minutes, 30 seconds. We still have no definite word on the condition of our bird. The data on our blackboards does not give us the figures we need to read out. Bill Schneider said that we do not have any definite word on our bird, but it does not look good at this time. 6 minutes, coming up on 7 minutes into the flight.
In case that was a little difficult to hear everything on the clip, I've got an explanation of what happened. 10 seconds before the two outboard engines were supposed to stop, one of them gimbaled and locked in a hard-over, pitched-down position. The whole combination, Atlas and Agena, flipped over into a nosedive and headed like a runaway torpedo back toward the Cape. Shortly after the booster engines stopped firing, the guidance control officer reported he had lost touch with the launch vehicle. Richard Keene, General Dynamics program manager for the Gemini Atlas, was alarmed and puzzled. Telemetry showed that the sustainer engine had cut off and a signal that the Agena had separated from its launch vehicle followed. In fact, Agena signals kept coming in until 456 seconds after launch. Then there was silence. Keene raced over to Hangar J, the General Dynamics data station, where the telemetry tapes pointed to an Atlas engine problem. But television reports implied that the target vehicle was in trouble again, and Lockheed officials winced whenever they heard someone speak of the Agena bird. This was ironic in the light of problems and delays caused by Atlas in the Mercury program and the success of Agena with Gemini 8. Meanwhile, the Gemini IX-A Atlas and Agena had plunged into the Atlantic Ocean 198 kilometers from where they had started. The Gemini IX-A flight with Tom Stafford and Gene Cernan waiting in the capsule had to be scrubbed due to the failure of the Atlantis to propel the target vehicle into orbit. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage spacerockethistory.com and clicking on the orange donate button or the Patreon link. Thanks.